Okay, here's video number 2 of chapter 9. This will be another kind of long video, but I want to finish up the topics and then go into some homework problems for you, some sample problems. I want to talk about colligative properties. colligative, colligative. It's a word that means collective properties. It means properties that depend only on the number of solute particles, not on the identity of the particles. The two we're going to concentrate on are freezing point depression and boiling point elevation. In the previous video, at the end, I was talking about this interesting concept called osmotic pressure, which is the pressure that's produced across a membrane that is called semi-permeable. And the semi-permeable membrane only allows water molecules to move left or right to the left. They move in whatever direction will equalize the concentrations that are on opposite sides of this membrane. So again, that is a colligative property like boiling point elevation and freezing point depression. It's a property that depends on how many of these little spheres, the solute particles, are dissolved per unit volume. It doesn't matter what they are. It's more of a physical property, not a chemical property. And the formula, interestingly, the formula that explains osmotic pressure looks a lot like the ideal gas law. Instead of PV equals MRT and PV equals nRT, it's pi equals, I believe it's MRT. So it kind of looks like the ideal gas law. Again, we're not going to treat this in a quantitative way. It's more of a conceptual argument. So I want to go back to review with you a little bit about what is a colligative property. And again, these aren't my normal colorful notes here, but they're from another class, but I think they're pretty easy to read. I hope so. A colligative property, as I said, means collective. So delta FP, which is called freezing point depression, that means change in something, change in freezing point. The change in boiling point are colligative properties of a solution. They depend only on how many solute particles are dissolved per unit volume. Some examples of colligative properties are antifreeze in a radiator, adding salt to ice to melt the ice. Why do we do those things? Well, it's because they create, they do two things at once. When you dissolve a solute like antifreeze or salt in a solvent, water being the solvent in this case, it does two things. It lowers the freezing point and it increases the boiling point of the solution. So it expands the liquid range of the water, which is what we want in a radiator. We want something in a radiator that has a very low freezing point and a very high boiling point. We add salt to ice in the winter because we want to lower the freezing point of the water so that it doesn't freeze. It freezes at a very low temperature. So here's how it works. It all has to do with the vapor pressure of the solution. Imagine you have a beaker filled with pure water. We'll call that pure solvent. And we know it boils essentially at 100 degrees Celsius. Well, let's say you took a solute, which we'll represent with these blue dots here. What happens? Well, the solute, the blue dots, does something interesting. It lowers the vapor pressure of the solution. So remember, the vapor pressure of a solution is caused by the liquid molecules evaporating and condensing at the same time. When water molecules evaporate, they create gas, water vapor, but sometimes the water vapor can condense back into the liquid state. When that's at equilibrium, you have the vapor pressure above the solution. So this almost has to be in a closed system, but I just drew it in an open beaker in this diagram. But you can imagine that the vapor pressure really is the pressure that you could measure above a liquid. In an open system, it might be kind of difficult to do. But we know that pure water boils at 100 degrees Celsius. If you dissolve something in the water, it actually boils above 100 degrees Celsius. Why is that? Why does the boiling point of the solution go up? Why is it higher than the pure solvent? Well, if you look at a close-up picture, this is the surface of the solution. What's at the surface of the solution now is not just water molecules, but it's a mixture of water and solute particles, these blue dots. So there's really not as many in the solution here. There are not as many water molecules at the surface to evaporate. So not as many water molecules at the surface means that the vapor pressure of the solution is going to be lower than the pure solvent. Please ignore these mathematical equations. We're not going to be dealing with those. These are for another class. But essentially what these formulas are saying is the vapor pressure above salt water here is going to be lower than it is here. So you can almost think of it like the blue dots, the solute molecules, whether they're table salt or sugar or antifreeze, they are blocking the water molecules and not allowing them to evaporate as quickly as the water would evaporate if it were a pure substance like pure water. So the boiling point of a solution might be can be as high as 110 degrees Celsius if you add enough of these solute particles into the solution. So the vapor pressure lowering is the key to the whole thing. And it really means you can calculate how much stuff is dissolved. And here, I'm going to show you this, but this is not in your chapter reading. It's just, I'll see if I can explain it without confusing you too much. So here's how it works. So this is a phase diagram. It shows the three states of matter, solid, liquid, and gas for any substance. The solid line represents the pure state, and if the vapor pressure is lowered, the whole graph basically drops to this dotted line. So when the vapor pressure of a solution is dropped, its phase diagram is shifted to this dotted surface here, and which means that the conditions under which it exists as a solid, liquid, and gas are now altered versus the pure solvent. Pure solvent. So that's the key to the whole thing. The boiling point is raised because vapor pressure of the solution is lower than the vapor pressure of the pure solvent. We usually express that as a delta T sub B. Again, you're not going to have to worry about that. This is just kind of a mathematical treatment we're not going to worry too much about. But again, another way to look at it is if you have at the surface of a solution, it's harder for the solvent S molecules to escape if there's something in the way. That's why the boiling point of a solution is going to be higher than the boiling point of the pure solvent. And it's the change in the boiling point, and the same goes for change in freezing point. This delta T is proportional to how much stuff you have dissolved, which is lower m here. The freezing point depression works on the same way. If you lower the vapor pressure of a solution, this dotted line here, it's now lower, you're going to alter the temperatures at which solid becomes liquid or liquid becomes gas. So again, I'm not expecting you to know how to read a phase diagram at this point. I'm just showing you where it kind of comes from. And one other interesting thing is how much of the freezing point is depressed or the boiling point is raised depends on the solvent. Each different solvent, whether it's water, benzene, or chloroform, they all have these different ways of responding to having something dissolved in them. Water, these constants are not too much of a concern for you, but it just is a reflection of the fact that different compounds, different solvents, respond in different ways to having something dissolved in them. So let me go to our discussion, how we're going to treat it, how we're going to look at it. We're going to look at it in a somewhat simplistic way. So when you have a solute dissolved, as I said, when you have a solution, okay, let's say we have this situation here. What happens to the boiling point? It increases. What happens to the freezing point relative to the pure solvent? It decreases. So and that is again proportional to how much solute you have dissolved. So the estimate we can use for us is that for every mole of solute that is dissolved per liter of water, now again, it doesn't matter what the solute is. All that matters is how many solute particles there are dissolved. So essentially you could call it the molarity of the solution. The higher the molarity, the more these effects are going to be observed. For every mole of solutes dissolved per liter of water, the boiling point tends to go up about half a degree for water. That doesn't sound like a lot, but if you can get an incredibly large amount of solute dissolved in a certain amount of water. So this explains, for instance, why the boiling point of calcium chloride solution, if it's 1 molar, is going to be higher than the boiling point of 1 molar sodium chloride. They both, you might think, well, won't they have the same boiling point because this is an ionic compound? That's an ionic compound. But if you look carefully, calcium chloride has the formula CaCl2, sodium chloride is NaCl. When CaCl2 dissolves, it breaks apart into 3 particles, 1 calcium ion and 2 chloride ions. So that's a total of 3. That's the most important part of this whole effect. It's how many particles you create. Really what is going back, remember, think back on here, the amount of osmotic pressure that was observed is proportional to how many of these circles are on either side of this membrane. The more circles, the more concentrated. So water flows left to right to equalize the concentration. So that's what's going on here with boiling point elevation. The more particles you can create in the solution, the more that particular salt is going to affect the boiling point of water, let's say. So it not only, calcium chloride would not only raise the boiling point of water higher than the 1 molar sodium chloride would, they're both the same concentration. This would have a greater effect on the boiling point than this because this creates more particles. That's really what we mean by a colligative property. It depends on number of particles. But it also will lower the freezing point more than the freezing point of the sodium chloride. Since more particles are formed here when this dissolves, this will have a lower freezing point than the sodium chloride. So to summarize, solutions always have a higher boiling point than pure solvents, and they always have a lower freezing point than the pure solvents. We can do some estimates here. This is kind of from your online textbook. If you can do some rough estimates here. Let's say water we know boils at 100.0 degrees Celsius. Can you predict roughly the boiling point of a solution? Here's your 3 solutions. You look carefully, you see they're not all the same. This is a salt that dissolves into 2 ions. So for every 1 of these, you get 2 of those. For every 1 of these sodium sulfates, you get 3 ions. For every 1 glucose, you just get 1 glucose. That's the difference between ionic compounds and molecular compounds. Molecular compounds do not ionize. They don't break apart. So the molarity of your solute doesn't change. The molarity of your amount of particles obtained from an ionic compound is going to be always larger than what you threw into solution. And so this is how you could do a problem like this. If you know that for every mole of solute that dissolves in a liter of water, the boiling point goes up by half a degree, you should be able to estimate the boiling points of these solutions if you just think about it from a numbers perspective. If you have sodium chloride, it breaks apart into 2 molecules. That's what this number means. And 2 times this number would tell you the number of particles, so to speak. 2 times 0.5 is 1. And for every 1 mole of particles, you raise the boiling point by half a degree. that's where that 1 times a 0.5 comes from. So the boiling point of a half molar solution of sodium chloride would be slightly higher, 100.5 degrees. You're like, big deal, half a degree. Well, these are small effects, but sometimes a couple degrees is all it takes to cause ice to melt in the winter. This is what we're doing when you throw ice on a sidewalk. You're lowering the freezing point of the ice so it melts. And this is why you're putting water in a antifreeze in a radiator. You're raising the boiling point of the water above 100 degrees Celsius. Now, if you compare the effect of half a molar sodium chloride with 1.5 molar sodium sulfate, the effect is more drastic. Sodium sulfate breaks apart into three ions. So 3 times this concentration is 4.5. 4.5 times 0.5 is about 2 1/4, 2.3. So that's why the boiling point of this solution, sodium sulfate, is actually higher than the boiling point of half a molar sodium chloride. 2 molar glucose would only raise the boiling point of water by 1 degree because glucose does not ionize like these two do. So 2 molar glucose would just be 2 moles of particles, and each mole of particle raises it half a degree. So if you have 2 moles of particles, you raise it by twice that number, which is 1 degree. That's why the boiling point of a 2 molar glucose solution would be about 101. So this is about the extent I'm going to expect you to be able to use these colligative properties in a mathematical sense. If I give you some sort of rough estimate for how much a solute affects the boiling point, moles per liter, can you predict the boiling point of a solution? You can use the same argument for freezing point depression. Now, I don't really talk about this, but why does adding a solute lower the freezing point? It's kind of easy to see why adding a solute raises the boiling point. So the solution has a higher boiling point than the pure water because when something boils, the water molecules have to escape the surface. If there's fewer water molecules at the surface to escape, then it's going to take a higher temperature to remove the water molecules from the liquid to the gas state. It's going to take more energy to push those out of the liquid state into the gas state. So the boiling point is going to go up because these blue dots represented by solute particles are in the way. They're not letting the water molecules evaporate as quickly as they would if they were just a pure solvent, 100% water. The same idea goes for freezing point. If you have something, when water freezes at 0 degrees Celsius, it means that the liquid water molecules are slowing down and they form a piece of ice. They condense into a solid structure. But if there's something in the way, if there's salt or sucrose dissolved in the water, the blue dots get in the way of the water molecules condensing into a solid. I should say solidifying into a solid. So to get the water to freeze and form a crystal, you have to lower the temperature even more than you normally would to freeze it. So that's why the freezing point of the solution is less than the freezing point of the pure solvent. It all has to do with the solute particles being in the way, so to speak, of the solvent molecules. So freezing point depression, for every mole of solute dissolved per liter of water, the freezing point is depressed about 1.9 degrees. So water responds in a more drastic way when its freezing point, when we're talking about its freezing point. Its boiling point is only raised about half a degree for every mole of solute dissolved. Its freezing point is affected about almost 4 times as much, but in the opposite direction. So for every mole of solute you dissolve, you lower the freezing point by almost 2 degrees. That's why solutions have a lower freezing point than the pure solvents. So let's see, can we use that knowledge to, for instance, give some explanation of which one of these has the lower freezing point or melting point. Remember, if I ask you something about melting point, it's the freezing point in the other direction. When something freezes, it goes from liquid to solid. When something melts, it goes from solid to liquid. That's the same point. Whether you're going from solid to liquid or liquid to solid, that occurs at the same temperature. It's either going to be increasing or decreasing. So for instance, if you look at a series of solutions, 0.1 molar sucrose versus 0.1 molar sodium chloride versus 0.08 molar calcium chloride or 0.04 molar sodium sulfate, they're all aqueous solutions. They're all ionic compounds dissolved in water or sugar water. The question is, which one of those has the lowest melting point and which one has the highest melting point? Well, here's the answer. And I won't explain it in too much detail. See if you can figure out why this is the case. The one that has the lowest melting point would be this one here, which would mean it would have the increasing melt. This has the highest melting point, which means it has the this has the lowest freezing point. Okay, this has the highest freezing point. So I guess I can give you the answer here of how you would do it, but you're just counting particles. So if you look at, take a calculator here, if you take 0.08, which is the concentration of calcium chloride, 0.08 times how many particles are released. When this dissolves, it makes 1 calcium and 2 chlorides, so that's 3 particles total. So 0.08 times the number of particles, 3, is 0.24. So that means that this solution would have its freezing point or melting point lowered 0.24. It has the most, actually I said that incorrectly. It has the highest concentration, 0.24. So this has 0.24 numbers of particles, so to speak. This guy here, 0.1 molar sodium chloride, sodium chloride breaks apart into 2 pieces, so 0.1, I don't know if you can see that on the screen here, 0.1 times 2 is 0.2, 0.20. Sodium sulfate, 0.04 molar. When that ionizes, it makes 2 sodiums and 1 sulfate, so that's a total of 3 particles. 2 sodiums and 1 sulfate is 3, so 3 times 0.04 is 0.12. 0.12. And this one is sucrose. While sucrose is a molecular compound, it does not ionize, so you just get 0.10 moles of particles. So you can see this calcium chloride has the most particles per liter. This sucrose has the fewest. So the one that has the most particles has the lowest melting point or lowest freezing point, whatever you want to call it. Then the next one up is this one, 0.2, sodium chloride, then sodium sulfate, and then sucrose. So I want you to be able to do that sort of analysis of a series of solutions. You have to look at the concentrations, look at what type of compound it is, ionic versus molecular, and then look at the total concentration of particles in the solution and list them from high to low, so to speak, if you're talking about freezing point. If we're talking about which one has the highest boiling point, this one would have the highest boiling point because it has the most particles dissolved in the solution. That's again what this colligative property is. It is proportional to whether it's change in boiling point, elevation, freezing point depression, or vapor pressure lowering. That effect will be proportional to how many particles there are. So try some of the homework problems in the textbook. I'm going to, in the next video, I'm going to give you, I'm going to go through a bunch of examples that will help solidify these concepts.